Now it's interesting in refrigeration. If you take a look at this picture here, right, here's work going into this. You know, you have a certain amount of QH coming out, and you have a certain amount of QL that's coming out as well. In the refrigeration, it's a reversal of the process. So QL and NW are coming in, and then QH coming out. So we're actually, you know, exchanging the heat. We're taking it from one place to the other. And they're doing the, you know, what's going on in the reverse. They're doing work. Heat is extracted from the cold and exhausted to the hot reservoir QH. When we look at entropy, entropy is a measure of a system's disorder. It's another way to look at the second law. All natural processes tend to move towards a state of greater disorder. And so we see that in everywhere in nature. And so, you know, if we put milk and sugar in the coffee, we're never going to get it out like it was before. Similar to that situation that we looked at with the glass or with, you know, the egg, right? Always, you know, going from order to disorder. And so, you know, like this glass, we take this glass, we throw it up onto the top of the table. It's not going to look good, right? It's going to be a mess. So the definition of a change in entropy, when a certain amount of heat added, is delta S equals Q over T. And so, you know, the total entropy of an isolated system never decreases, and so it always increases with an isolated system. And so let's take a look at some situations here. All right, well, let's go ahead and define these, right? So the change in entropy is a joule per Kelvin, right? So, and then Q is heat going into the system, and then T is Kelvin temperature, average temperature for the process, and the key here is average temperature. The heat going into the system, let's say you're cooling the system, then you'd have negative Q in there. And if the change in entropy is positive, then randomness or disorder has increased, right? So, you know, if you have liquid water and you're heating it up and it's turning into gas, it's going to be disordered, right? Spontaneous changes involve an increase in entropy, right? So natural processes is going to more disorder. And entropy can only go down when energy is put into the system. And so, you know, if you're decreasing entropy in one area, you're increasing in the other. And the overall process, if you consider the whole thing, you know, it's an increase in entropy. All right, so this is M13. What is the change in entropy of 0.29 kilograms of water at 5 degrees when heated to 100 degrees? And then part B, how much more entropy change for the continued warming until all the water becomes steam? So if you want to pause the clip, and this, you know, it's going from 5 degrees to 100 degrees. Again, you're going to need to have temperature in Kelvin. You know, you can do the first part with MC delta T, and then let's actually, yeah, I want you to see if you can go through the whole thing, and then when ready to check, you can hit play to continue. So go ahead and pause the clip and give this a shot, and then you can check in a second. Okay, so we should get for the heat going in. It's going from 5 degrees to 100 degrees. 4186 is the specific heat, so that's Q going in. And then when we look at the entropy change, we know how much heat went in. The average temperature, right, is 100 plus 5 over 2. That's the average temperature. We add that to 273, and that will give us the average temperature Kelvin. So the overall entropy increase would be 345. 0.4 or 0.299 joules per Kelvin. How much more entropy change if we continue to bring this all the way to steam, right? So the latent heat of fusion we've got here. So this is the amount of heat that it would take to make it actually change into water, water to become steam. And we know that that temperature is going to stay at 373. You know, it's 100 degrees plus 273, then we have that there. So 1754 for a total of 2108 joules per Kelvin. So when we consider natural processes, we know that things get colder, right? Things can be more ordered. So let's take a look at a situation here where we have a mass, 90 degrees Celsius mass placed into 10-degree water, and we want to find the overall change in entropy. So if we consider that, right, this mass is going in there, we know that this mass is going to cool down, and therefore the order is going to be more, right? But again, when we're considering the entire system, we have to consider everything, right? And what's the change in entropy of everything. So, what we're going to have to do first is figure out, what's going on with the temperature, right? Here's the mass, 1.24 kilograms. Specific heat of the copper is 390 joules per kilogram degrees Celsius. Initial temperature is 90 degrees. We have the water here, which is 0.73 kilograms and 10 degrees Celsius. So, we know that we're going to need the average temperature eventually, right, to be able to look at entropy. So the first thing we got to do is calorimetry. So go ahead and pause the clip and figure out what the final temperature would be, and then we'll move to the entropy part. All right, so sum of the Q's equals 0. We've got those, and so we should get a final temperature of 20.931 degrees Celsius. Now that we know the final temperature, we can look at the entropy change for both the copper and the water. We're going to do both here. So once you see if you can do that, go ahead and pause the clip and try this here. And when you're ready to check, you can hit play to continue. All right, so we'll use this one for copper. We'll use this one for water. And we have MC delta T. We know the mass of it, we know the specific heat, and we know the difference in temperature, final minus initial. And we'll end up getting a change of negative 101.69 joules per Kelvin. For the water over here, we have 0.73 times 4186. We have the final temperature minus the initial temperature, and that's over the average temperature, which we have there. And so we get 115.795. So when we bring those together and we add those together, we get an entropy change of 14.1, right? So this means that even though, this became more ordered, right, negative 101, this became more disordered and more than this, right? And so the overall entropy change is positive, and that's going to be true for any natural process. So you can have a decrease in entropy from one part, but in that other part, it's going to compensate and be a greater entropy change.